All right, thank you for the introduction and to the organizers for inviting me. So today I'll talk about the limits of quantum learning. It's a little bit of a more general title than was on the program. And in some ways, this talk will pick up in the general context that Una talked about in the first part of her talk a few hours ago, in terms of this kind of grand open question of what features of quantum states and dynamics we can learn from modern AMO and quantum computing experiments. And unlike a lot of the talks in this week, which are about all the exciting, new, and useful and insightful things we can do with machine learning and neural networks, my talk will be coming at it from a slightly different direction. So trying to understand the fundamental limits of what we can ever hope to learn from quantum experimental data. And I'll show that actually what we can hope to learn is maybe a little bit less and a little more challenging than we might naively have thought. And the hope is by understanding this, it can help guide us in where to kind of productively focus our efforts moving forward. So I want to start with a kind of broad introduction, because I know there's people here from lots of different backgrounds. The big question that will motivate this entire talk is, given experimental access to a big quantum system, what can we learn about it? So this is a very, very general question. In some ways, it's kind of the entire history of physics and observation. And as we've discussed, this dates back to, in some ways, the earliest days of quantum mechanics. We're doing experiments on big quantum systems. We're gathering data, and we're using that to learn properties about these systems and quantum mechanics itself. And of course, over the many decades, over the last century, we've developed much more interesting quantum experiments, especially in condensed matter and material setups. And we've developed many new ways of gathering lots and lots of interesting data from these experiments. But the real kind of focus of today and the experimental context that has brought this particular question to the forefront is modern quantum computing experiments. So increasingly today, we're able to realize highly coherent and controlled quantum experiments of hundreds and hopefully soon thousands of individual qubits or atoms. And the key feature of these experiments is they're not only large, but they're very coherent and controllable. And so this allows us to realize and manipulate quantum states and dynamics that we previously never dreamed of, that would have been impossible to realize in a more natural physical context. And it also gives us brand new ways of reading out information, of measuring and extracting information from those states. So instead of measuring just some simple coarse-grained local observables, we can measure entire bit strings that come out of some quantum state. Or we can take a quantum state or dynamics and perform some interesting computational algorithm on top of that state and read out something even more interesting and unusual than just measuring in the simple computational basis. And so, this new world we're living in has raised a lot of questions as to, what we can hope to learn about quantum states and dynamics with these new abilities. And I want to list, again, just because I know it's a broad audience, some of the main questions and topics people have been thinking of along these lines. So one really basic question is about benchmarking. So say I've prepared some quantum state or dynamics on a quantum device, and I want to learn, what the fidelity of that state is with the state I had hoped to prepare. So this is a very basic question just to getting these systems working as we hope they are. And there's been lots of actually really interesting research about new and unusual protocols for extracting the fidelity and performance of quantum devices, such as cross-entropy benchmarking and techniques like classical shadow tomography. Once we've gotten these systems working as we hope they do, we hope to use them to answer fundamental physical questions. So one very long-standing question we might hope to answer in new contexts is something as simple as, what is the phase of matter of some quantum state, say a ground state of some Hamiltonian? And this has sparked lots of interesting algorithms. We'll hear about one, actually, I think, from Sunwon this Friday. Quantum algorithms to learn the phase of matter of different states. And there's been a lot of work and progress on rigorously understanding the success of these algorithms, where they work and where they might fail. We can also ask kind of new questions entirely. So this has been a very popular thing, especially in many-body dynamics the last decade or so, about new properties of quantum states related to entanglement and complexity in quantum information that were completely hopeless to measure in the past, but now increasingly can be measured in quantum experiments. And there's actually a lot of back and forth and progress in understanding what information or complexity theoretic properties are or are not observable with different types of quantum experiments, including many recent works on using things like neural networks to help us observe these properties. And finally, there's also some hope that we can use quantum experimental data to help us train classical simulations of quantum states and dynamics themselves. So there's been really nice works on using quantum experimental data, say bit strings that come out of some quantum experiment, to learn a tensor network representation or a neural network representation of the quantum state in the device, and hoping that this can help us improve our classical simulation methods moving forward. So there's been tons of progress here. I've flashed a few key ideas, but there's also been some challenges along the way. So for example, in some of these benchmarking and fidelity estimation protocols, in almost every one of the kind of general protocols we have, one requires a classical simulation of the state that we're trying to benchmark against. And this is a big limitation, and it makes these protocols unfavorable and infeasible for the complex states and dynamics we actually hope to eventually explore. In estimating information theoretic properties, there have been lots of recent progress in finding that some algorithms fundamentally break down or contain a very unfavorable scaling with some parameters for learning these properties. And finally, in learning representations of quantum dynamics, there's been lots of progress, especially for ground state problems, but there's also been lots of challenges, especially in many-body dynamical problems, and even algorithms like neural nets that in principle can simulate highly entangled states tend to fail, in some cases, rather quickly in practice. It's a big challenge to get them to succeed on entangled quantum dynamics. And so the goal of this talk is to kind of approach this from a different side and understand fundamentally what we can ever hope to learn from quantum experiments. So to understand the limits of quantum learning. And we'll do this by jumping way to the far end and asking a sort of provocative but very fundamental question, which is, are there situations when we can learn absolutely nothing about a quantum system from experiments on it? And so in the rest of this talk, I'll tell you about a few works we've done over the past year or two, trying to answer this question in various contexts. And I'll start with one work together with Jonas Haferkamp and Robert Huang that came out about a year ago, which showed that actually there are many quantum systems that are very hard to learn anything about, and they're a lot more common and physically relevant than you might think. And then in the latter half of this talk, I'll talk about some recent progress on trying to understand how this original result intersects with physical systems that we more commonly encounter in the physical world. All right, but I'll start with this result. You might have heard it from me or Jonas or Robert in the past, but it'll kind of help build the intuition and context for these later results as well. Okay, so we're trying to answer this question. When can we learn absolutely nothing about a quantum system from experiments? So what do I mean by this? So say I have some quantum circuit I'm trying to learn about, call it U, and consider a completely, absolutely general quantum experiment I could do that involves some quantum circuit or dynamics U. So I prepare some initial state, I apply the dynamics, I do some operation, maybe a circuit on it, maybe measurement and feed forward, then I apply the dynamics again, I do another measurement, more feed forward, I apply the dynamics again, and so on. So a completely general quantum experiment. And we're going to ask, are there circuits, systems U, where I can learn absolutely nothing about them from any experiment of this extremely general form? And so this might sound like a very vague and abstract question, but it in fact connects closely to something you all are intimately familiar with. So if you go to NumPy and you call numpy.random.rand, you get a sequence of pseudo-random numbers. And there's a guarantee when you are delivered those numbers that from just the numbers you get, you can learn absolutely nothing about the distribution that they came from. So under some standard cryptographic assumption, the numbers you are given are indistinguishable from completely random numbers. Random numbers contain no information, so you can learn absolutely no information from the numbers you are given. And so from this intuition, we can phrase this question a little more precisely in the quantum context as follows. When can a quantum system, say some time evolution or circuit, look completely random? And so to make this a little more precise, there's a simple definition of when a unitary operation looks completely random. So a Haar random unitary on n qubits is just a completely random 2 to the n by 2 to the n matrix drawn from the so-called Haar or uniform measure on u of 2 to the n. And when we say, does a quantum system look completely random, we mean does the output of any possible experiment involving that system, is that output indistinguishable from the output we would have gotten on the same experiment if the system truly was completely random. So if we cannot tell the outputs of any experiments apart, we'll say it looks completely random, a very physical definition. And so people have studied this actually for a long time, over the last decade or two, and they've come up with very precise ways to quantify when a system looks completely random. It's not too important to understand the details, I just want to tell you the definitions so that you know people have studied this. So the most long-standing way people have quantified this is with something called a unitary K-design. And a circuit is a unitary K-design if it looks Haar random in any experiment that queries it K times. So if K is 5, it applies U, does a circuit, applies U, does a circuit 5 times. And if the output of any of those experiments looks the same as if you were Haar random, we say it's a unitary K-design. In some applications, we care about the number of queries being very large. Like you might want a lot of data, say to train some interesting neural network or attack some cryptographic problem. And so people have also developed a sort of stronger in some ways notion called a pseudo-random unitary. We say that a circuit is a pseudo-random unitary if it's indistinguishable from a Haar random unitary in any polynomial time quantum experiment. So any experiment that queries U some polynomial number of times in the total number of qubits, say n squared or n to the 5 or n to the 10, and also does just polynomial depth quantum operations in between. And so people have thought about these objects for some time, and prior to our work, so about a year ago, there was a very common broad intuition about precisely when quantum systems can look completely random under these definitions. And zooming out a little, kind of merging several results in just 2 bullets, the rough result, the belief, is that in 1D systems, things can look completely random in linear time, scaling linearly with the total number of qubits n. And in all-to-all connected systems, they can look completely random in log n time. So exponentially faster, leveraging that all-to-all connectivity. And for a long time, we believed these were, as fast as anything could possibly look random, because these scalings are super intuitive. So for example, 1D circuits require linear depth to generate high entanglement across any cut, or to have light cones that touch every qubit in the circuit. And similar arguments show that classical circuits always require linear time to appear completely classically random. So it seemed reasonable that quantum circuits might require these times as well. And so in this work from about a year ago, we showed that actually something very different happens in quantum systems. So we proved that local quantum circuits can form unitary K-designs and pseudo-random unitaries, so they can become indistinguishable from Haar random unitaries, in just above log n time in one-dimensional systems, and just above log of log n time in all-to-all connected systems. So both of these are exponentially faster than we previously thought. And so just to kind of highlight the take-home, these circuits are generated by very low-depth circuits and very short-time evolutions. They're very low complexity, and they create only geometrically local short-range entanglement. And yet we prove that they're indistinguishable from completely random unitaries, which generically have exponential complexity. And due to time, I won't go into the details of our construction or proof, but I would like to remark that our construction of these objects is not some crazy fine-tuned thing. It follows from a kind of very simple and general fact we prove about how local uncertainty and randomness in quantum systems propagates to global uncertainty and randomness. So it's our belief, we prove our results in some context, but it's our belief that this is a fairly general phenomenon of structureless quantum systems. I'd like to go over a little intuition behind this result and then discuss some connections back to learning. So why do these quantum systems behave so differently than the behavior we already knew in the classical world? So I'll give you a super rough intuition, very rough but kind of helpful. So in a classical experiment involving some classical random circuit, there's only one source of randomness, the circuit itself. So we're doing some experiment, and there's only one source of uncertainty in that experiment. It's our lack of knowledge about the circuit we're given, our lack of knowledge about the pseudo-random number generator that NumPy is using behind the scenes. But in a quantum experiment, there's really two sources of randomness. One is the circuit itself. Say if I'm given some unknown dynamics and I don't know what they are, there's some notion of randomness from my lack of knowledge of that, just like in the classical context. But there's also a new source of randomness from random measurement outcomes. So if I take a quantum state and I measure it in the wrong basis, a basis that does not commute with that state, then I receive completely random information, which reveals no information or properties about the state or dynamics I'm trying to learn about. And in some ways, what's happening in the circuits we construct is that these quantum systems are using non-commuting observables they're hiding information into non-commuting observables in a way that this measurement randomness is allowing us to mask a lack of randomness in the circuit itself. So because of this sort of new fundamental source of uncertainty and randomness in quantum experiments, they're able to appear globally random much faster than a classical system ever could. So it's a very rough intuition, but just to give you some feel for where this difference comes from. And so just to address some common things you might think about, yeah?
Does that mean the measurement is always in, let's say, the Z basis?
No, your measurement can be in any basis you so choose, and it could be a very fancy basis. But the key is you don't know about the dynamics, so you don't know what's the good basis to measure in. And it turns out it's very hard to find that good basis because you keep guessing the wrong one and learning no information. That's the rough idea. And so just to go over some common things you might try to distinguish some low-depth quantum thing from a completely random quantum thing. So you might try to measure the light cone of the circuit, because the light cone of some shallow log-depth circuit is very small. You might also try to measure the entanglement of the circuit, because it's also not so large. These are not very entangled quantum states. You might even try, if you wanted to be really aggressive, to just learn all the parameters of the circuit itself. This is something a lot of people have studied in the last year or two. But if you look up, people have studied all of these problems. Some of them are very simple, actually. If you look it up, all of the methods to learn these properties scale exponentially in the depth of the circuit or quantum dynamics you're interested in. So as soon as that depth is just above logarithmic in system size, the scaling of all of these methods is greater than any polynomial in the number of qubits. So it's infeasible at large system sizes for any quantum or classical algorithm. So what implications does this have for learning? The most basic implication is almost just the problem statement itself. So our result shows that very relatively short time quantum dynamics with a circuit depth or time growing just above logarithmically in the number of qubits, can become completely indistinguishable from exponentially late time Haar random dynamics. So this provides a very fundamental limit on our ability to observe a very basic property, just the time of some quantum evolution. Our results also have some other implications. For example, that training quantum variational circuits very rapidly becomes hard from generic starting points. So this follows from lots of works in this field I'm sure you've all heard about, which rely on the resemblance of kind of generic variational circuits to Haar random unitaries. So if we now understand that that resemblance sets in much earlier, these difficulties also will set in much earlier. It's also, this is a bit less direct, but it also has some implications for the hardness of classically simulating even quite shallow quantum circuits. So in this field of quantum supremacy via random circuit sampling, our best arguments for the classical hardness of simulating random circuit output probabilities arise from the resemblance of these circuits to completely random unitaries. So again, knowing that this resemblance sets in much earlier than we expected also implies that this classical hardness sets in much earlier. And there are many more applications that I won't go into, some to the power of time reversal in quantum learning, some to more efficient protocols for classical shadow tomography, and other implications in more physical and quantum information theory contexts. And so, in the second half of this talk, I'd like to discuss some follow-ups, so what we've been thinking about since this result. And these follow-ups stem from a pretty simple question that kind of bothered me when we were originally working on this result, which is that everything I just told you suggests that generic quantum systems should very rapidly become completely indistinguishable from, useless, completely Haar random dynamics. And this would be very bad if it was true. It would mean we can't learn anything about these systems, and we've shown it can happen very fast. And we think that lots of the quantum systems, either in the lab or in the physical world, actually share some properties with structureless random dynamics. Lots of studies in quantum chaos and physics suggest that generic quantum systems should share some properties with these random circuits that we studied in our earlier work. So if this is true, why can we observe anything in the physical world? Looking out clearly, the history of physics tells us we can learn lots about physical systems, and there's lots of very rich data to learn from. How does that intersect with this result I just told you about, that systems can, in principle, lose all observable features very rapidly? And so, if you think about it, okay, this question is actually not so complex to answer. At least some very naive answers would invoke physical symmetries. So we know that ground states in the physical world often obey some symmetry constraints, and these are very fundamental to their behaviors and classification. So we study, phases of matter, at least in its original study, is based on how systems, break or don't break physical symmetry constraints. And so perhaps maybe symmetries lend some structure to states in the physical world, to ground states, that make them easier to learn. In the context of dynamics, kind of a similar thing might arise. So dynamics in the physical world often feature conserved quantities like charge or energy. And the fact that these quantities are conserved leads to long-lived physical behaviors, which means that we certainly have properties to observe. We can just measure where is the energy, where is the charge of the system. So this just immediately prevents them from looking completely random, like in the first half of this talk. And so maybe, so this is the concrete question we'll tackle, is maybe the presence of physical symmetries prevents this fast formation of random unitaries. So we'd like to understand, how do these random unitary behaviors intersect with physical symmetries? And so now in the remainder of this talk, I'll tell you a little bit briefly about some of our recent progress on this. First, in the context of ground states and recognizing phases of matter. And second, in the context of quantum dynamics. And In the ground state context, just to give a little preview, our results will show that actually a lot of this fast emergence of random behavior still sets in, even in the presence of symmetry. And this will leave a kind of open question as to why we can efficiently learn ground states in the physical world. So I'll get to that more. In the second context, we'll show that a more interesting story emerges for dynamical problems with conserved charge and energy. And yeah, sorry, I'm swerving a little bit, but we'll get to it. Okay, so let's start with this first question. So symmetries and quantum ground states. So we've all learned in grad school or undergrad that phases of matter in many body systems are classified by their patterns of symmetry breaking or fractionalization or entanglement. And so as a very simple example, for a system with a simple, say, Z2 cross Z2 symmetry, there are there are many possible phases of matter we might have, but here are 4 examples. So for one, we could have a trivial phase, which just respects both of these Z2 symmetries. A slightly more interesting one would be a ground state that spontaneously breaks one of these symmetries. For example, a GHZ state. A third sort of even more interesting example would be a symmetry-protected topological phase, like the cluster state, with respect to this Z2 cross Z2 symmetry. And a fourth example, maybe even more interesting, which doesn't in principle rely on this symmetry, would be something like a topological phase. So something with some interesting pattern of entanglement, and it might or might not intersect with these symmetry operations. And so we have all these nice examples of different states displaying different phases of matter. And in our modern theory, especially from a quantum information point of view, these phases are classified by their equivalents under local unitary circuit transformations. So we say that one quantum ground state is in the same phase of matter as another quantum ground state, if and only if it's connected by a low-depth symmetric local unitary circuit, or time evolution. And so with this definition in hand, a very natural question that we can try to address is, given experimental access to some quantum state, how can we determine what phase of matter that state is in? And you maybe can already see where I'm starting to go with this, because I've told you lots of results about low-depth circuits becoming completely random, and now I've told you that our classification of phases of matter is built on equivalence under low-depth circuits. So what we prove in this recent work is that even in the presence of any discrete on-site symmetry, so Z2 cross Z2 or any other discrete on-site group, quantum circuits can become indistinguishable from symmetric Haar-random unitaries in the same depths as before. So in just above log n depth in 1D systems, and just above log n depth in all-to-all systems. So very similar kind of headline result, but with a kind of more disturbing implication now. Because what this implies is that for every phase of matter, trivial, symmetry breaking, SPT, topological, under discrete symmetries, there exist quantum states for which recognizing their phase of matter requires computational resources growing exponentially in the range of correlations C of that state. So the proof is incredibly simple. It's just super straightforward. Say we take any fixed point state of any phase of matter, and we apply a shallow, symmetric, pseudo-random circuit to it, like the ones we construct in our work. So what our results prove is that the resulting state cannot be distinguished by any polynomial time experiment from a symmetric Haar-random state, which has no structure, basically no properties to observe. And so, what we can show is this hardness of distinguishing these two grows exponentially in the range of correlations C of the state. And this just immediately becomes super polynomial in the number of qubits n as soon as this correlation length C is greater than log n, just like in our previous results. And log n is not so big. Log n with, say, 10 to the 23 atoms is 23. But that's not that big a correlation length. And for smaller systems, it's of course even smaller. And so, this sounds very surprising, but once you think about it more, it's kind of very clear actually what's happening in our results and where this both kind of does and does not intersect the states we actually see in the physical world. So what's happening to our results can be illustrated, say, with this simple example of just taking a GHZ state. So say we take a GHZ state and we apply a low-depth symmetric random circuit to it. So this GHZ state, it's easy to measure its phase of matter because we just measure some long-range ZZ correlations. And if these long-range connected correlations are large, then we know we're in a symmetry-breaking state. Now, after we apply some low-depth symmetric circuit to this state, it still features long-range correlations because that circuit was very shallow, very low depth. But these correlations are no longer observable with simple one-body Z operators. They're instead contained in some moderately non-local, random order parameter generated by conjugating the Z operator by this random circuit. So what happens is these systems do feature genuine long-range correlations signaling symmetry-breaking order, but finding these order parameters is hard for any polynomial time quantum experiment. And a similar logic applies to SPT phases with string order parameters and topological phases with, again, string-like order parameters, and even trivial phases. The fact that they're connected to a product state is rapidly obscured by this low-depth random circuit. And so I know this has been kind of brief, but I want to close this section with just kind of the takeaway from this result, which maybe you've already sensed, which is that this is really a worst-case statement in the sense that we're showing there exist quantum states whose phase of matter is perfectly well-defined. They have genuine quantized long-range correlations, but is computationally hard to recognize in any experiment. Maybe just some brief comments. So the states we realize, they do not resemble ground states in the physical world in lots of key ways. So for example, in this symmetry-breaking state, real ground states in the real world don't have pseudo-random order parameters. They often have pretty good overlap with very simple one-body order parameters we can easily measure. And so I think looking forward, this raises an interesting question, which is, if not symmetries, what properties of physical systems in the real world guarantee that their phases are so easily recognizable? I think there's lots of clear intuition on this question from, say, CFT and so on. But from a more rigorous quantum information point of view, I think this is actually a pretty open and not well understood question. And so with the remaining, say, 5 or 10 minutes, I'd like to briefly talk about this final result, which will hopefully come out sometime soon, which again thinks about how these random unitary behaviors intersect with symmetries, but this time more in the context of quantum dynamics. So if we think about why dynamics in the physical world are interesting, one very, very simple reason is that physical systems have conserved quantities. So say a physical system might conserve the total charge or number of particles in its state, or it might conserve the total energy or some more interesting quantity. And what this means is that these systems just manifestly cannot relax in this fast logarithmic time from the beginning of the talk. Because it takes, quadratic time in a 1D system to diffuse charge or energy from one side of the system to the other, or linear time if that transport is ballistic. And so naively, this suggests that all of our results just immediately break down. And maybe one can learn lots of features of interesting physical dynamics at early times. So we wanted to study this in more detail. So we considered a very, very simple toy model, which is just a system with number conservation. So we'll think about the most simple conserved quantity possible, just conserving the total number or charge of particles in some state. So as I said, the diffusion of charge immediately implies that we need very long times for a physical system to look completely random. And the question we tried to ask is, what can one learn about charge-conserving circuits at these earlier times? So does this open the door to much more interesting and rich learning strategies. And what we prove is that, in fact, no. So it'll take me a minute or two to unpack this result. But what we prove is that charge-conserving quantum circuits can become indistinguishable from maximally random dynamics with the same transport of charge after just log squared n time. So what do I mean by this? So as I said, the diffusion of charge, charge can only move locally. And so any low-depth charge-conserving circuit necessarily can be distinguished from a very deep, completely random circuit by just looking at how it moves charge. But say we fix that simple degree of freedom. Say we fix that some circuit has to move charge in some simple local manner. And then we ask about all the possible unitary operations that could move charge in that manner. And that's actually a very big space of possibilities. And most of it are very complex, highly entangling dynamics. And what we prove is that actually even this very simple and low-depth quantum circuit conserving charge can become indistinguishable from these exponentially complex random unitaries that move charge in the same way. And a kind of interesting consequence of this is that we can show that no polynomial time quantum experiment can distinguish a quantum from purely classical charge conserving process after just log squared n time. So in other words, one can only learn the classical charge distribution of the system and nothing else. So this, of course, this notion of classicality in charge is very specific to the specific conserved quantity that we've considered here. But I think the interesting thing about this is it kind of maybe hints at how these random unitaries ideas intersect with physical systems in the real world. So in the real world, we have lots of conserved quantities, and they can display lots of different interesting behaviors. They don't just have to diffuse, they can have lots of interesting transport that we can detect. But these results suggest that maybe the behavior of those conserved quantities is roughly all we can detect. And all of the more interesting and maybe information theoretic properties of these quantum dynamics can rapidly become completely unobservable in very quick times. So there's some separation between the simple degrees of freedom that are easy to observe and more complex degrees of freedom which rapidly become unobservable. So that's all. I know is kind of brief and high level, but hopefully I gave you some feel for our results on these questions. Again, the kind of big takeaway is simply that short time and low entanglement quantum dynamics can rapidly become much harder to learn than we naively expect. And I think there's lots of interesting questions looking forward with this, such as what properties of ground states lead them to their phases to be efficiently observable? How can we generalize from these very simple toy models with number conservation to more interesting physical systems? And if there are more positive applications of these results, perhaps do more versatile, say, classical shadows and benchmarking protocols. So thank you all for your time.
Well, maybe, I don't know if there are any,
Well, maybe you can use it because it's a little hard to hear.
Oh, okay.
Yeah.
Okay. It sounds a little suicidal. Your talk, it became more and more suicidal as it goes. But I wonder if it is like, you want to say something about physical something, system, world, physical something. But physical systems dynamics are not random unitary. Why are you guys so hung up on random unitary, which seems suicidal? Like physical systems dynamics are given by Hamiltonian, that's what Schrödinger taught us.
Yeah.
And Hamiltonians are not random unitaries.
That's true.
So, like, why are you digging yourself deeper and deeper into this?
It's a fair question. We're doing it because, well, for one, I'd start by saying for the ground state problems, and I tried to emphasize this, I think they're poor models. Like for phases of matter, I think they're constructing kind of artificial states that are showing that our common definitions of phases of matter are not precise enough to capture the reason phases are easy to learn in the physical world. So for that, they're bizarre counterexamples that teach us that we need to refine our definitions. For dynamics, and this last and the earlier point, There's actually lots of evidence in physics that for highly entangling quantum systems, even at finite temperatures with Hamiltonians and physical structure, a lot of their features actually are pretty well modeled by random unitaries.
Give me a material.
I'm not a material scientist, so
Okay,
that's hard.
give me a system, physical system that I can put on my hand.
Okay, like say Google has done some, there's lots of examples, but Google has done some recent experiments in an
These are
analog.
all within quantum simulators.
They're within quantum simulators.
Right.
Yes, yes.
It's a very restricting.
That's true.
The whole
Okay.
entire physical world to be all quantum simulators. It's very, very narrow.
Okay, but say we take these quantum simulation experiments where we can probe very precise properties. We see that actually a lot of these properties, say the fluctuations of bit strings in these systems, the entanglements, information, and so on, do bear some resemblance to random unitary predictions. They're not the same, but there's ways we can adapt these random unitary ideas to capture Hamiltonian dynamics as well. Now, in a material, I mean, this is what we're trying to get at a little bit at the end. In a material, surely the system still is very entangling. You know, there's tons of entanglement generated very quickly. And of course, in a material experiment, we can only read out very, certain quantities. We can't read out as much as in an analog quantum simulation. But what these are trying to tell us is even if we could read out so much more, like we can in quantum simulation experiments, it might not bias drastically much more. Like a lot of the features that we can't learn in materials experiments, we also won't be able to learn in much more powerful quantum computing experiments because they might just be fundamentally hard to learn. That's my perspective.
Okay. I think I saw another question over here. That's still an active question.
I'm not sure it is. Yes. Now, I need to think. I will find you later.
Okay.
Yeah.
Shall I?
Sure. Maybe you can give him the microphone.
Oh, yeah.
Pass it to him.
I'm trying to understand this in a time scale. So when you say it's hard to distinguish it from a random unitary, if I just work hard on doing it, like how long should I?
Yeah.
It's like a complexity of time.
The complexity grows exponentially in the time. That's basically as simple as it is. So once the time is bigger than log n, the complexity is bigger than e to the something bigger than log n, which is greater than any polynomial in n.
Okay.
Yeah. Okay.
Do these properties exist under noise?
Yeah, I mean, sorry, I'll wait. That's a good question. I mean, so you can ask the question would be, does the way, in some ways the answer is yes. Like the way a short depth random circuit reacts to noise is very similar to the way some exponentially complex thing will react to noise. The behavior will change in both cases, but it'll change in the same way from this result. So things like how sensitive XEB and various benchmarks are to noise is explained by these results. Tamara? Yeah.
Okay, so I am having trouble getting a sense of how concerned I should be about your results. And
Yeah.
in particular, I think I'm failing to see the precise setup in which you prove these statements. So for example, in the case where you're trying to distinguish what phase you're in,
Yeah.
you do that after application of like a random circuit. So
Yeah.
it's almost like you're introducing randomness and then you're saying at the end of that, I can't distinguish it from it being random in the first place. Similarly with the comparison of charge-conserving random circuits to a particular dynamics that conserves charge, are you assuming any particular additional structure? Like how are you able to do that comparison so that you can make the statement that, it looks random without being random? I guess I'm failing to see this similarly in the first case. When you're, I guess, trying to show that you get something that forms K-designs or pseudo-random K-designs. Yeah, I'm failing to see the particular setup.
Yeah, that's a great question. So in some ways, all these results are on kind of toy model scenarios. in the sense that, like, as you say, like in the real world, say I fix some Hamiltonian, I want to learn its properties. There's just one Hamiltonian there. And in principle, so this is the kind of tricky part, is if I knew that Hamiltonian, I already know everything I need to know in principle from a kind of information point of view. So, but in the real world, we don't know how to compute many properties of this Hamiltonian. And we might even not have precise knowledge of that system. Like there's lots of situations where I might be looking at some, say, molecule in nature, and I don't know its precise structure, and I want to learn that. So this is kind of a model in some way, where we're introducing randomness as a model of our lack of knowledge about some physical system, or our lack of ability to compute its properties. And there are precise contexts where we provide some very precise circuits where, with lack of knowledge about this circuit, everything is provably very hard to learn. And then there is a leap of faith on whether you believe or don't believe that models physical systems. And I think what I was trying to go at earlier is, I think for these ground state problems, they're really kind of bizarre counterexamples, and they should not be taken seriously for at least typical systems we see in the real world. I think for dynamics, actually, there is some evidence that these are good models. But yeah, that step is a leap of faith that requires lots of physical studies and so on. But these show kind of what could be possible in adversarial settings, I would say. Yeah.
Okay. Last question.
Okay.
All right, so let me just make sure I'm understanding one of your earlier slides. So you're basically saying if you had some system which conserved charge, then you could essentially highly obfuscate a system, but the charge eventually could be obtained, like the original classical charge. Is there any symmetry that wouldn't survive, that after you obfuscate it, or any conserved quantity, I should say, not symmetry, that wouldn't be able to re-obtain?
Yeah, so our results don't say that, they actually say you can learn the charge. So we're not really obfuscating the charge. We're saying you can't learn anything else. Everything else is very hard.
So what I'm asking is, are there any conserved quantities, maybe highly unusual and artificial quantities that you're really stretching to do that you wouldn't be able to do that?
Yeah, it's a good question. At some level, we don't know, because we chose the simplest example for things we could really show. For general continuous symmetries, like of a finite size, I think it probably still holds. Maybe when you have lots of them, I don't know. For things like energy, my guess is similar results would hold, but that's really unknown at a theoretical level. Yeah.
Okay, so in order to stay on time, let's thank Thomas for a very nice and engaging talk.